this anti-integrable limit is godsend. It just makes it so simple that who would think that the nonlinear field theory would be simple? I think it just gets worse and worse, right? But it turns out that limit is simple, just like small perturbation around Keplerian ellipses and harmonic oscillators are relatively simple in the beginning. Right now, just have to get comfortable with the idea that that's how strong coupling theory looks like. Now, I'm totally baffled myself because 5-4 theory is what everybody would write. And the way they think about it, they say, well, if it's quantum mechanics, it's some kind of, wave functions that obey these path integral weights, equations, whatever. And nobody ever says that these are fractals and points. But if you say, let me first solve the classical equation exactly first, then I didn't expect it, but you sit on a very rarefied set of, very small part of the state space, which are these points that sit on this very rarefied fractal. Fortunately, the structure you can describe in great detail accurately. That's what these pictures will do, that the Shonker will produce. I didn't expect that. This comes like, I just thought we would be finding points everywhere, and then we would put some wave on them, and we would get approximation to quantum mechanics. That was correct. I didn't expect that there would be just so few of them. that baffles me. I still don't understand how does that work. But that's what it is. We took 5-4, we discretize it. Everybody does that. And the only difference that we say is, we say, let's first find out all classical solutions, which are the saddle point of pathing. So everybody also thinks that's okay. That's what Gutzwiller theory is. And that suddenly is sitting on a very small subspace of, it's just very few points compared to the volume, but that's what it is. These points are this Cantor says that survive some number of iterations, little rectangles, and there are very few of them. Amazing. What can I say? Mathematics says that's what it is. We have to understand it. And then when you go, because you're looking at translational invariant things, so you have to take Fourier spectra, because whenever you have something translation invariant, you have to look at its representation, irreducible representation, that's called Fourier spectrum. That one is going to be some kind of fractal and not usual band structure of condensed matter physics. So it's same surprise looked at twice. In space, it's a fractal, and it's Fourier space, it's also a fractal. I find it totally surprising.